This is the Chapter 11 Stoichiometry Practice Test Walkthrough. So for the reaction shown here, if I begin with 138.6 grams of potassium chlorate and it decomposes, how much oxygen gas by mass would be produced? Okay, so we're going to use the boxes. The first thing that we have is we're given 138.6 grams of KClO3. So that goes in the first box here. That's our known, so I'm going to put KClO3 in these places, the first two boxes in the bottom of the mole ratio in the middle, so I can keep track of what's going where. And I need the molar mass of the known, so I'm going to add up the 39 grams for potassium, 35.5 for chlorine, and 48, which is oxygen's mass times 3, for a total of 122.5 grams. And that goes on the bottom of the left-hand box. So I'm going to divide 138.6 by 122.5, and that will give me the answer that goes in the second box, which is the number of moles of potassium chlorate that I have. So now I have converted grams to moles, and now I need the mole ratio. In order to do that, I need to identify my unknown, which the question says is oxygen gas. So that's O2 in the equation. And in the equation, it has a coefficient of 3. I'm going to put O2 on all the other boxes because that's my unknown, so just to keep track. Okay, so I'm going to put a 3 in the top of the mole ratio, which is that middle box, because that's the coefficient for the unknown. The coefficient for the known is 2, so I've got 3 over 2 as a mole ratio. And then I multiply 1.131 times 3 over 2, and I get 1.697. That's the number of moles of oxygen that I'm going to get. The question asked me for mass, so I need to multiply the moles times the mass of O2. Oxygen is 16, so O2 would be 32 grams. So 1.697 times 32 gives me 54.29 grams. Remember on the test, show your work. If you round differently and you get a slightly different answer, I need to know it's because you rounded and not just because you got the wrong answer somehow and I don't know how you got it. Okay, same equation for number 2. How many grams of O2 will be produced if 87.5 grams of potassium chloride are also produced? So we're looking at two products this time instead of a reactant and a product. But the process is exactly the same. First, what's my known? I'm given 87.5 grams of potassium chloride, so I'm going to put KCl for potassium chloride in the 3 boxes for the known. And I'm going to put 87.5 grams in the first top left box because that's what I was given. Then I need the molar mass of potassium chloride. So 39 plus 35.5, that's potassium and chloride, or chlorine, gives me 74.5 grams. So that goes in the bottom of the left-hand box there. And I divide those two numbers out to get 1.17 moles of potassium chloride. Now I need my mole ratio, so let's identify the unknown. In the question, the unknown is how many grams of O2, so the same unknown that we had the first time. So I'm going to put O2 on those boxes again. And the coefficient is the same, it's 3 for O2. 3 is the coefficient in the equation, and the coefficient of my known, which is KCl, is 2. So it's actually 3 over 2 again, just like it was in the last problem, even though we're dealing with a different substance. So 1.17 times 3 over 2 gives me 1.76 moles of O2. But again, the question asks for grams, so I have to multiply that by 32. That's the mass of oxygen. And I get 56.3 grams of oxygen. Okay, next question. This time we're going to liters of O2, or we're starting with liters of O2 rather, and we're going to grams of potassium chlorate. So we're going to set this up essentially the same way. The only difference is that in the first box, okay, we're going to put 53.5 liters. And we need to remember that 1 mole is equal to 22.4 liters. We're going to assume this is standard temperature and pressure since it didn't say otherwise. So I'm going to put 22.4 where I would normally put the molar mass. I'm going to put the molar volume, which is 22.4 for any gas at standard temperature and pressure. And I'm going to do 53.5 divided by 22.4 gives me 2.39 moles of oxygen. And from here, it's just like every other problem we've done. Okay, I'm going to take the coefficient of my known, which is 3. That goes in the bottom of the mole ratio. My unknown, I'm trying to find potassium chlorate. So the coefficient there is 2. I'm going to put potassium chlorate on all the other boxes to keep track. So 2.39 times 2/3 gives me the moles of potassium chlorate, which is 1.59. And then to get to grams, because that's what the question asked for, I have to do the molar mass of potassium chlorate, which we did once before. It's 39 plus 35.5 plus 48, 122.5. So 1.59 moles times 122.5 grams gives me 195 grams of potassium chlorate would be produced, or would be needed in order to produce 53.5 liters of O2. Okay, this is an energy heat question. Okay, we have now added into the equation the number of kilojoules on the left-hand side. 1970 kilojoules are required for this reaction. So this is an endothermic. When the heat or energy is on the left-hand side, that's an endothermic reaction. It needs to add heat in order to get the products, instead of having heat as a product. So how many kilojoules of energy are needed to produce 721 grams of potassium chloride? So we're going to do this mostly like we've done all the other problems. We're just going to do a couple of things slightly different. We're actually going to do less steps than we've done before in the last two problems. So our starting point is 721.2 grams of potassium chloride. So that's my known. Put that on those boxes. Drop in 721.2. And then I take the molar mass, which is 74.5 of potassium and a chlorine, add it together. That goes in the bottom of the first box. Divide that out to get to moles. And it's almost 10 moles, 9.68 moles of potassium chloride. Now here's where it's going to be a little bit different, because kilojoules, we're not talking about terms of moles, but the number of kilojoules in the equation can be treated as a coefficient. So since kilojoules, oh actually I'm going to do, sorry, potassium chloride is my known, so that coefficient is 2, that goes in the bottom. On the top goes kilojoules, okay, and the kilojoules is 1970. That's the coefficient, just like it would be 2 moles of KCl. It's 2 moles, or sorry, 1970 kilojoules. So I'm going to put that number right on the top of the equation, because for every 1970 kilojoules, I get 2 moles of potassium chloride. So it works the same way as the other mole fractions. It's just a bigger number. And then I do the same thing. 9.68 times 1970 over 2 gives me 9,535 kilojoules, and I can actually stop here because I'm not converting kilojoules into anything else. The question is about kilojoules, so I can stop there and skip the last couple boxes. Okay, 183 grams of fluorine. How many grams of, actually that's going to be NH3. All right, so our known is 183.0 grams of fluorine. A molar mass of 38. Okay, so then I'm going to do 183 divided by 38, and I get 4.816. That's moles. That's my known. It goes on the bottom. And I'm trying to find ammonia. Ammonia is my unknown, so that goes in all the other boxes. And the coefficient of ammonia in the question is 2, or in the equation rather is 2. So multiplying the number of moles times the mole fraction, 4.816 times 2 divided by 5 is 1.926 moles of ammonia. And the molar mass of ammonia, it's nitrogen, which is 14, plus 3 hydrogens, which is 3, so 17 grams. Gives you 3.275 grams of ammonia, rounding to 4 significant figures because our starting number over here had 4 significant figures. Okay, same equation. How many grams of hydrofluoric acid or hydrogen fluoride are produced by the reaction of 82.4 grams of ammonia? So our known is ammonia. That's what we're given. And that goes down here. And we're starting with 82.4 grams. And we just said that the molar mass was 17. So I'm going to put that on the bottom. And we're going to do 82.4 divided by 17. And we get 4.85 moles, and then we need to do the mole ratio. So our known was ammonia. That has a coefficient of 2, which goes on the bottom, and we're looking at our unknown, which is hydrogen fluoride, and in the equation that has a coefficient of 6. So 6 over 2, 4.85 times 6 divided by 2 is 14.6 moles. rounding to 3 significant figures there. And then the molar mass of hydrogen fluoride is 20, fluorine is 19, hydrogen is 1. So we're going to do 14.6 times 20, and that's 292 grams. All right, now we have a limiting reactant question because we're given not one, but 2 reactants to work with. So the easiest way to figure out which is going to be the limiting one, which will tell us how many grams of product we're going to get, is just to do the whole thing twice. We're going to start one problem with the 23.3 grams of aluminum. So aluminum is going to be my known. On the bottom, I'm going to use CuSO4 as my known. In both cases, aluminum sulfate, and I'm just going to write it on the first box here, is my unknown. Okay, so that's true in both the top and the bottom set of boxes. The difference is, okay, so on the top I need the mass of aluminum, which I'm going to use 27 grams. And I'm going to say 23.33 divided by 27 is 8.64. It's actually 8.641 for significant figures. Okay, I'm going to carry this out to this box over here for both, and then we'll see which one we need to continue with. So the mole ratio, aluminum has a coefficient of 2 in the equation. Aluminum sulfate has a coefficient of 1. So 8.641 times 1/2 is 4.321. 4.321. How about that? So that's the number of moles. So I'm going to stop there for now, and then I'm going to go back and look at the copper sulfate. So the molar mass of copper sulfate is 63.5 for copper plus 32 for sulfur plus 64 for oxygen, which gives me 159.5 grams. So if I do 74.44 divided by 159.5, I get 4.667 moles. And my mole ratio here, copper sulfate, way up here in the equation, has a coefficient of 3. Aluminum sulfate still has a 1 coefficient. 4.667 divided by 3, or times 1/3, gives me 1.556 moles. Okay, so I can stop here with the top number because I can see that I've got fewer moles of aluminum sulfate in the bottom. That's going to give me the smaller answer. That's my limiting reactant. So now I need to do the last 2 boxes down here to find my answer to this question, number 6, how many grams. So aluminum sulfate is aluminum times 2, so that's going to be 54, plus sulfur times 3, so that's 96, plus oxygen times 12, which is 192. Oops, that's 92. Okay, and that gives me 342 grams times 1.556 is 532.2 grams. Okay, rounding to 4 significant figures because that's what we started with. So the answer to the first part of this question, or to question 6, is 532.2 grams of aluminum sulfate. Now the next question is, what's the limiting reactant? Well, the limiting reactant was copper sulfate, okay, because that was the one that gave us the smaller answer. How many grams of the excess reactant are left over? So here's sort of a tricky question. So the excess reactant was aluminum, because that wasn't the one that ran out first, according to our numbers. So what we're going to do is first find out how many grams are used, and we're going to do that by doing the boxes down here, starting with our limiting reactant. 74.44 grams of copper, and we said in the last problem that that gives us 159.5 as a molar mass and 4.667 moles of copper sulfate. Now, the coefficients in the equation, let me erase some of the stuff up here to clear out this equation. So now we're looking at copper sulfate and aluminum. Okay, the coefficient of copper sulfate is 3 and aluminum is 2. Aluminum is our unknown because that's what we're trying to figure out right now. How much aluminum gets used up? And copper sulfate is 3. So 4.667 times 2 divided by 3 is 3.111 moles of aluminum. And we said that aluminum has a mass of 27 grams. Okay, so 3.111 times 27 grams is 8.3. It's actually going to round off to 8.400 grams. Okay, so that means, what this means is that when I used my 74.44 grams of copper sulfate, I also needed to use 8.4 grams of aluminum with it to create the 532 grams of product. The question is, how much excess aluminum do I have? Well, according to the question originally, I had 23.33 grams of aluminum to start with, and according to this, I used 8.4 grams of aluminum. So how much do I have left? Well, I have 23.33 minus 8.4, which is 14.93 grams of aluminum left. That would be what was left over once the copper sulfate ran out. That's the question. Okay, so we've got a percent yield question. We have to start by finding the theoretical yield. So the theoretical yield, we're going to start with 150 grams of sodium chlorate, NaClO3. The mass of that is going to be 23 plus 35.5 plus 48. 48 plus 35.5 plus 23 is 106.5 grams. So 150 divided by 106.5 is 1.408 moles of sodium chlorate. How many grams of O2 would I theoretically get? My mole ratio. My known is sodium chlorate. It has a coefficient of 2. My unknown, how many grams of oxygen, has a coefficient of 3. So I would do 1.408 times 3 divided by 2, and I get 2.113 moles of oxygen. Oxygen has a mass of 32. It's 2 oxygens, 16 each. So 2.113 times 32 is 32.00 grams. 2.113 times 32 is 7.61 or 62, rounding it off, grams of O2. That's how much I should get theoretically. Okay, so there's obviously a little bit of a typo here because according to this, our actual yield is greater than our theoretical yield, which can't happen. But I'm just going to carry this out the way I would if it wasn't a typo. So the actual yield says 68 grams, and I put that over the theoretical yield, which is what I get in this question above, which is 67.62 grams, and then I'm going to multiply that by 100 to get my percentage, which is actually going to be something greater than 100%. 68 divided by 67.62 gives me 100.6%. Another percent yield question asked a little bit differently. Okay, this says instead of giving the actual yield to find the percent yield, it gives you the percent yield and you have to find the actual yield. We can do that. we're going to start out everything the same way. We're going to do the stoichiometry to find the theoretical yield. 51.0 grams of ammonia, NH3. It has a mass of 17 grams, a nitrogen and 3 hydrogens. 51 divided by 17 is exactly 3 moles, 3.00 moles to be precise about it. And the mole ratio, we've got ammonia as our unknown, so that's 4. Water is our known, that's 6. So 3 times 6/4, 4.5 moles of water. Water is 2 hydrogens and an oxygen, which is 18 grams. So 4.5 times 18 says that our theoretical yield is 81.0 grams. That's how much we should get. According to the question, we only got 94% of that. The way to figure this out is we have 81.0 grams times 0.94, which is what 94% would be as a decimal. 76.1 grams. Oldies but goodies. This should say nickel, protons, neutrons, and electrons. Does this isotope have? Well, it's nickel with 28 on the bottom and 62 on the top. So the 28 on the bottom tells you that there are 28 protons and 28 electrons, since this is a neutral isotope. And the 62 on the top tells you that it's got a mass of 62, and the mass is made up of protons plus neutrons. So if we just take away the protons from the neutrons, we take away the protons from the mass, we get the neutrons, which is 34. So 34 neutrons, 28 protons, 28 electrons. All right, number 12, the formula for cobalt-3 fluoride. Okay, cobalt-3 fluoride tells you that you've got cobalt with a +3 charge. Fluoride is fluorine, which always has a -1 charge. So to balance out the charges, I need 1 cobalt and a total of 3 fluorines, or fluorides. Okay, so the 3 fluorides give me a total of -3 to balance out the +3 of that 1 cobalt. Identify the type of reaction. Well, the first one, you have to look carefully. You've got 2 compounds on both sides. So that rules out synthesis and decomposition. I don't have oxygen as a reactant, so it's not likely to be combustion, but just to be sure, I've got 2 compounds where the partners trade places. Okay, the chlorine and the nitrate, or the sodium and the silver, depending on how you look at it, both trade places to form 2 new compounds. 2 compounds as reactants, 2 new compounds as products where the halves have been switched is called double replacement or double displacement, depending on where you see it. Both would be correct. Those 2 are interchangeable. And this one here, in this case, we've got zinc trading places with hydrogen. This is actually single displacement. All right, so make sure you know how to do your stoichiometry boxes. You will be allowed to use the whiteboards with the stoichiometry chart on it during the test. You'll have a periodic table. The rest is up to you. We'll see you tomorrow.